Hey, folks, welcome once again to the Monday live stream on EarthSky's YouTube channel. And today we are going to be sitting down with Tereza Constantinuou. Teresa is a PhD student at the Institute of Astronomy at the University of Cambridge in the United Kingdom, which is way the heck over there. And actually, no, it's way the heck over there. Sorry, I got turned around. And she is working on the history of Venus with Professor Oliver Shortall and Dr. Paul B. Rimmer. And their research her research explores the interdisciplinary intersection of planetary sciences, habitability, and astrobiology. And she and her co-researchers just last week in Nature Astronomy published a dry Vesuvian interior constrained by atmospheric chemistry. And that's what we're going to be talking about today. Venus, ancient Venus, wet or dry. So, hi, Teresa. Welcome. How are you today?
Hello, thank you. I'm doing good. Thanks. How you doing?
I'm doing well. It looks like it's nighttime there in the UK.
Yeah, though it begins to be nighttime at around 3 p.m. now, so.
Oh, God. That's something else. Well, I'm dressed for the weather here because I'm stuck inside a 300-mile long fog bank. The Thule fog has arrived with the winter. Okay, so we're talking today about Venus, and why don't you tell us what Venus is like? People say that it's Earth's twin, which it is. It's about the same size. I mean, almost exactly the same size, but they're very different places. Tell us about those differences? What's the difference between Venus and Earth?
Yeah, I mean, you're right. Earth and Venus are often thought of as twins or sister planets.
Mm-hmm.
And that's mainly because they're very similar in mass, and radius, and density, and distance from the sun. But they're kind of evolutionary paths that diverged dramatically. So Venus now has surface conditions that are extreme compared to Earth. It's got surface temperatures soaring to around, I only know in Celsius, around like kind of 460 Celsius. And then it's got an
Which
atmosphere.
melts lead. That will
Yeah,
melt lead.
exactly. Yeah, that would melt lead. And it's got a pressure that's 90 times greater. So to get that sort of pressure here on Earth, you have to be a kilometer underwater. And then it's also got a really toxic atmosphere, mainly carbon dioxide, and it's got sulfuric acid clouds. So a very different world from
Yeah,
Earth.
but other than that, just like Earth.
Yes.
Well, you know what? It has some other things that are going on, right? Its day is extreme, isn't it? It's an extremely long day. 243 Earth days to the rotation, right?
Yeah.
And it doesn't go the same direction as us. It's going backwards, right? It rotates so that the sun comes up in the west and sets in the east, why is that? Do we know why it's rotating like that? Do we have any idea? Does it have to do with the lack of a moon, maybe?
There's, I think, lots of ideas, in fact, as to why that's happened. It's not entirely sure, but that's more to do with how the planet formed much earlier on.
Okay, so it's just the way things fell together in the early solar system, and that's what we're talking about right now. Yeah, we got a hot planet that's slowly rotating, and it's very, very close to the sun, extremely hot. So our stage is set. So you guys wanted to look at how can I put it? It used to be the standard knowledge, or the standard idea, let's put it that way, was that Venus at some point had surface water, maybe oceans, a temperate climate, and is turning out that maybe that's not true. That's what your paper says, right?
Yeah.
So what were you looking for? What were you looking for? And where did you get your data? Let's start right there.
Yeah, we were essentially looking for any clues of Venus's past climate and what Venus looks like today. So whatever imprints that the past climate might have left behind, we were just looking for it. So far, climate modeling has been crucial of informing our picture of an early Venus. So it's essentially the climate models that we would use today on Earth to predict the weather tomorrow. We use that for a very early Venus. So wind the clock.
Okay.
for
Wind the
Venus.
clock back and we look at the climate of Venus and
Yes.
we created a model from that, right? Is that what you're saying? Or okay. And so where did you get your data, first of all? Where did you get your information about Venus? We can't just go out and get your standard Venus data set. It has to come from someplace.
Mhm. Yeah, I mean, what we've used is we've used kind of data from atmospheric observations. So that's a mixture of, there's been some past missions to Venus, like Venera, that kind of went to Venus and collected lots of samples that told us about
Mhm.
what the atmosphere is made out of.
Okay.
But also, we've got ground-based telescopes that have been observing Venus throughout the years, every now and then, pointing them to Venus, seeing what we can see. And again, from that, we can kind of get information about what the atmosphere is made out of.
Okay, so that's what we're looking at right now, what the atmospheric composition is. What is it? What is the atmosphere of Venus like? What's in that toxic mix besides a lot of sulfur gas?
It is mainly carbon dioxide, which is
Oh,
partly, or rather, which is exactly why it is so hot. We know here on Earth, carbon dioxide is a
mhm,
greenhouse gas. We're trying
right.
to avoid putting much more into the atmosphere because it's warming us up. But that's
Hmm.
what's happened on Venus. Like
Ah,
96% of the atmosphere is carbon dioxide, making it really, really hot.
okay. So we had a question from Brad. I'm probably going to mispronounce your name, Maji. Oh, maybe I didn't. Asked if it wasn't for the toxic atmosphere, would Venus support human life, or is it too close to the sun? He wants to know. I don't know if that's within your range of expertise. I kind of think it's no because of the pressure, but
Yeah, you would have to change a lot of things about Venus to make it hospitable to human life. So it's not just a toxic atmosphere, like I said, it is also the pressure that is 90 times what it is here on Earth. So we would not really be very comfortable at all.
no.
But it is just too hot. It is, Brad is correct. It is just too close to the sun. It is way too hot for us.
Okay, so the CO2 isn't toxic, so that you can leave the CO2, but you're still going to have a greenhouse effect. You're still going to
Mm,
have the 400 degrees Celsius temperatures that just make it fairly unpleasant for a human being.
mhm.
So, anyway, so you guys were looking at specific kinds of gases that still appear in Venus's atmosphere, but Venus loses its atmosphere and it has to be replaced.
Mhm.
So, that reveals the interior of the planet to you, doesn't it?
Yeah, exactly. So essentially, what we were trying to do with this piece of work is we were looking for a window to peek inside the planet, so in the interior of the planet,
Hmm.
because we've realized that each of the two kind of climate past theories that have been proposed for Venus, and that is one Venus kind of being like Earth with oceans, temperate climate, like you've said, and the other
Hmm.
Venus being basically what it is like today, hellish hot. These two kind of theories leave a very different imprint on the inside of the planet. Now, if Venus was once
Oh.
habitable, that would leave kind of a water rich interior of the planet.
Hmm.
But if Venus was never habitable, if it was always this hellish, hot, born this way, that water inventory would have been depleted way earlier on in its lifetime and would have left the inside very, very dry. So essentially, we're looking into the atmosphere, trying to find a way to peek inside the planet to see what the composition is made of. Now, we do the same thing for Earth. To understand
Oh,
what is inside Earth, we often look at
yeah.
volcanoes. We look at what comes out of a volcano because it's coming directly from the inside of the planet. So we try to do the same for Venus.
Mm,
We try to look
okay.
at what the volcanoes are spewing out and see how much water is in there to tell
So
us about
Venus is very is it active volcanically?
that.
Very
So
much. Okay.
that is also kind of new discoveries within that. So we know that the surface is made like, mainly of basalt. So it's covered in
Okay.
pieces of lava. And
Right.
we
That's
can
a
see there's
lot of
volcanoes
extruded
on
rock.
Venus. Yeah, there's volcanoes on Venus that we know of. It has been tricky and so far to tell whether there's still volcanism going on to this date. But there
Hmm.
was another paper earlier on this year that looked at some kind of radar images of the surface and it kind of observed lava flowing essentially. So yes, we know that
Oh,
there is currently volcanism in Venus, which is very exciting.
okay. So we have a source for sampling the interior gases now. We have volcanism.
Exactly.
And what did you guys find? What's the result here? What were the gases that your study revealed?
Yeah, so we're looking at any gases, like you said, that needed to be kind of replenishing the atmosphere that's being
Hmm.
destroyed. And from that, we saw the volcanic gases, and we compared that to volcanic gases here on Earth.
Oh,
Now,
okay.
the gases on that Venus's volcanoes are releasing are about 6% water. But if we were to kind of put Earth's interior on Venus and let it do volcanism, that interior would release kind of 96% water.
Oh, well, that's a bit
So,
of a difference then, isn't it?
right, yeah, way more wet. I mean, even if you look at
Oh
volcanoes
my.
here on Earth, if you've ever seen, like, I mean, if you're lucky or kind of unlucky, if you see it in person, a volcanic eruption, or
I've
if you've
seen them
seen
on
the
TV.
photos, yeah. But like you see these kind of large billowing clouds coming out of volcanoes,
Right.
and most of
Uh-huh.
that is water.
Oh, that's it's water vapor that's been turned into steam and then condensed back into water as it
Exactly, yeah.
spews out into the atmosphere, carrying all that ash and
Mm,
yeah, super hot gases. And it's very unpleasant stuff, those pyroclastic flows, extremely hot and very fast.
mhm,
You cannot outrun them. We
mhm.
had Mount St. Helens happen when I was a kid right up
Wow,
here.
yeah.
Boy, that was something else to watch. So so that's going on today on Venus, and it's going on here. And when we look at the gases at the on the two different locations, we see something vastly different. On Venus, 6% water
Mhm,
vapor. On
mhm.
Earth, what was the number you said? What was the number on
I
Earth?
mean, on Earth, it's around maybe half of the water. It depends on where your volcano is, but
Oh,
in
well,
this
yeah.
case, if we just take the inside and put it on Venus and let
Uh-huh.
it do its stuff there, because it depends on what the surface pressure is like and things like
Oh,
this. So if we did that on Venus, it would be around 96%.
wow. Okay. So that means that Venus doesn't have any interior water. Well, it has some. It has a small amount of interior water.
Mhm.
So, is it enough to have been a water world at some point, or what do you think?
I think
What's the
no.
end? No, you think no?
No, so it's not so much that it never had enough water as a whole
Oh,
planet. I think it still could have very well had a huge kind of water inventory. So it could have been born
oh,
with an ocean amount of water, if not more. It's just
mhm,
it ended up being slightly too close to the sun. And because of that, so when planets first form, they're magma oceans. So essentially, the surface is lava everywhere. It's all still
mhm,
too hot from formation.
right.
Because Venus was just so much closer to the sun, that kind of magma ocean stage took way longer to cool down.
Oh,
Kind
oh,
of
well, that makes
hot
sense.
lava surface for much longer. That
Right.
essentially means that any water it had was only in its atmosphere as steam. Now, when you have gases in your atmosphere, they are exposed to the UV radiation from the sun. Now, UV
Mhm.
radiation has lots of energy. It can actually break up water molecules.
It
So if you
sure
have
does.
if you have kind of steam in the atmosphere and you have the incoming UV radiation, that breaks up your water molecules into hydrogen and oxygen.
Oh,
Hydrogen, very light element, can
and
escape
off it
the
goes.
atmosphere. So if
Right.
you had all of your water inventory only in your atmosphere, it would be broken up into hydrogen. The hydrogen would escape, and it would leave this kind of very hydrogen poor, water poor planet. And that's what we've observed on the
And
inside
that's
of the
what we're
planet.
seeing.
That's
So
what we're
yeah, wow. So it sounds like it makes sense to me that Venus and Earth would have had in the earliest period of the solar system very similar compositions because we're talking about drawing from the same source material. In fact, we just
Mhm,
had Astor Taylor, whose work is on dark comets, and he's discovered there's still a lot of what appear to be wet comets
mhm,
flying around, and they could have been, maybe, we don't know, more research needed always, a source of water. It could have been an early
mhm.
source of water. So we had, if you're interested in that, we talked with Taylor. Ooh, it's been a while, but it's back in our archive on YouTube. And that reminds me, this is a good point for me to remind everybody that we will be back on Wednesday to talk about the Geminids meteor shower, and that'll be at 1815 Universal Time. But then on Friday, Deborah Bird, EarthSky's Deborah Bird, will sit down with C. Alex Young, who is our resident heliophysicist, and he's at the NASA Goddard Flight Center, where he studies the sun and presents that sun news for us every day. Well, almost every day. But on Fridays, he sits down with Deborah and they talk about the latest sun news for the week, what's coming up, what's happened, what we've seen. Always some great images and great information. And that's Friday, 8 at 1815 Universal Time. And but meanwhile, we're on Venus. Let's go back to Venus and Teresa. So, where were we? We were talking about the sun, and the sun is putting out its solar radiation, and the hydrogen is deconstructed from the water, and it's light, and it's floating, and it's blown away by the solar radiation. The solar wind is
Mhm.
shooting it off. All that hydrogen is gaseous out in the solar system. What happened next? Where did we what happened after that to poor old Venus? It really got a beating, didn't it?
Yeah, it did. Essentially, that just means it kind of was slowly losing its water budgets over the years.
Hmm.
Now, this meant that it was kind of always this hot, hellish world that we know of today. In fact, in that case, if it did have kind of a large water inventory earlier in its life and it did have that steam atmosphere,
Hmm.
that would have made it even hotter
Oh,
because water is also a greenhouse gas that also
yes, it is.
contributes to the heating. And climate modeling, that is, like we said, wound back the clock and see what the climate would look like. They did this with this kind of huge water inventory, and they found that in this case, clouds would form kind of permanently
Oh,
on the night side of Venus. Now, what this means is on your day side, you're exposed to the sun, you've got all this incoming radiation warming up your planet, and then if
hmm,
you have clouds on the night side, they reflect the heat back in. So they kind of trap the heat inside of the planet. So that led to like 700 degrees Celsius. So much, much hotter than it is today. I think twice as hot as Venus is today. So in
right.
fact, it was even more hellish earlier on in its life.
That's hard to imagine. And of course, the context here is that a Venusian day is 243 Earth days long. So when it's exposed to the sun, it is not a short event. It is a
Mm,
very long event. Wow. And so the eons passed and the water was gone. And
mhm,
now we have CO2. The CO2, that's, I guess, geological. Is that what we don't have a venugeological?
mhm.
So it's a geological source, and this is all coming from volcanism. And
Yes, exactly.
that's what the paper says, is that it's likely that Venus did have a similar composition to Earth. It really was our twin at one point, much
Mhm,
more so, but it picked the wrong neighborhood. Location, 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 guys.
mhm.
Always location, location, location. Got to be in that Goldilocks zone. So Venus never had water on the surface then? Probably. We can't say for sure, but what do you think?
I mean, I think no. Given
Mm.
how dry the interior is, then it's not really consistent with Venus ever having oceans, ever having that kind of cool temperate climate to condense
Because
them.
the water would have seeped into the surface of the planet if it had stood
Yeah.
on the surface. Okay. So now we know this, and it's kind of important to know this because we're exploring the solar system. This is a much different uh, set of circumstances than we're finding on Mars, for instance, where supposedly if you dig up a 5 gallon bucket of Martian soil, about half of it might be very saline, but water bearing, you know?
Mhm.
So what does your research tell us about other worlds? What can we expect? How does this support the ongoing exploration of our solar system and the solar systems beyond ours?
Yeah, I
Where
mean,
are we going?
kind of like you said, Venus, Earth, and Mars, they provide this natural laboratory almost for studying how habitability, or the lack of it,
Mhm.
evolves. So it helps us understand what it took for Earth to become habitable and host us versus what it took for its twins to become, so Venus hellish and Mars kind of cold and dry.
Mm.
And like you said, this is not just important for exploring our solar system, it's also important for looking at exoplanets and exploring
Mhm.
beyond, especially because most of exoplanet science is now kind of driven or motivated by searching for other habitable worlds, if not inhabited, and searching for alien life. Um, Now, instruments that we've got now, like the James Webb Space Telescope, are best at studying the atmospheres of planets close to their host star, so Venus like planets, Venus analogues.
Mhm.
So, if Venus was habitable in its past, then it would mean that the other planets that we have found or are currently looking at have the potential to be habitable and be candidates for kind of looking for life. But if Venus was never habitable, then it makes all these Venus-like exoplanets that we're detecting and studying less likely candidates for habitable conditions or for life. So it kind of means we just need to narrow our search
Right.
when looking for life to planets more like Earth or exo-Earths.
It's important to know where not to look for life too.
Exactly, yeah. If we want to kind of have the best odds at finding something, especially with limited
Right.
budgets and
Yeah, no kidding.
observational time.
Yeah, we only have so much money, so many telescopes, and the
Yeah.
universe appears to be bounded but infinite somehow.
Mm,
Well, so there's a lot to look at. And that's so as an astrobiologist, that is so cool, by the way, an astrobiologist.
mm.
Are you looking for ET, or are you looking, what are you're obviously looking, hoping, I think that would probably be your greatest dream is, oh my God, look, I found it. I found it. Speaking of which, there's one more thing I'd like to plug, and that's a week from today in this time slot, so 1815 UTC, I am going to be talking with, where is it? I'm going to be talking with Burkhard Militza, and he is another planetary specialist, and he thinks that Uranus and Neptune, the gas giant planets, may have a distinct ocean as a layer within their composition. So it might be a core and then some kind of gaseous boundary, maybe. And then on top of that, a separate liquid ocean that is isolated by the conditions of the planet. At least that's what he thinks he's seeing. And he's got his research together. And we'll be talking to him about that next Monday right here in this slot. But right now, we're on Venus and we're exploring the solar system with Tereza Constantinuou. I surely hope I'm saying your name correctly.
Hmm?
Okay, so anyway, when you're looking for ET, you're not looking for UFOs, you're not looking for green guys with antennas walking around making beep beep noises to scare the locals. What you're looking for is signs of life, gases, things like that. What are you tell me what you're looking for, because I don't know.
Yeah, usually what we're looking for is, like you said, gases. So gases that result from our metabolism. So a good example here on Earth is oxygen, because the only reason we have so much oxygen in our atmosphere is because of photosynthetic life. So all the
Mm-hmm.
plants and trees kind of producing all this oxygen. So if we were to look for life in our solar system, if we looked at Earth and we saw this oxygen, then we'd think, that could be a sign for life. But it becomes way trickier when you're dealing with non-Earth-like life, because it's
Mm-hmm.
kind of easy to know what life is like here and what it's producing. So say plants produce oxygen and look for oxygen, but
Mm-hmm.
that is very specific to life as it's evolved here. And to be fair, that was a theory for a while for Venus. There's been some recent news and findings of some gases in Venus's atmosphere that we can't really explain otherwise. So there's
Hmm.
potentially phosphine being detected. And the only reason that scientists have been able to come up with as to why there is phosphine on Venus is maybe through metabolism. Maybe life is producing.
Biological process.
Yes,
Wow. So
yes.
maybe there are some extremophile bacteria
Mm,
and very simple organisms living in the atmosphere or buried in the soil. Because I know here on Earth, the biosphere extends at 5 to 10 kilometers below the surface,
mhm,
depending on which part of the planet you're on, which makes the life very protected from those big cosmic events, like the oxygenation event you mentioned earlier, when suddenly
mhm,
the atmosphere was mostly oxygen and almost everything died as a result. So
mm.
anyway, we didn't kill them all, folks. Wasn't us. Um, anyway, so you're looking for trace gases, signs of metabolism. What else? What
Mhm.
else do we? What hints? I mean, because oxygen is obvious for us, but what if it's a silicon-based life form that breathes methane? Is that going to look different, or how do the what other signatures? What clues are you giving us?
Yeah, I mean, that's when it becomes way trickier. Essentially, the kind of end member of looking for life on other planets, especially exoplanets, is if we're able to have kind of biogeochemical models that can explain all abiotic processes happening on a planet and we just
Mhm.
let it run. So if we have a model that describes everything that happens on Earth that is non-life related and let it run and then see what it looks like then, see the atmosphere and compare it to what its atmosphere actually looks like. So if we were to do that for Earth, you wouldn't see so much oxygen because that's all
No,
produced from life.
right.
However, if you compared it to what you're seeing, you'd see all this oxygen. So you'd think, oh, where is this coming from? This is not in any of kind of my models. None of these abiotic processes like volcanism, the ocean, plate tectonics, atmospheric chemistry, whatever, none of these can
Mhm.
explain this. So there must be something else out there. But even then, you never know if it's life or if it's any sort of other chemistry going on or geochemistry going on that you kind of don't really know.
Sure is tantalizing, though. The clues
Mm.
might be there. And that's what your research is doing. Your research is helping us eliminate non clues and pointing toward the clues that may lead to the discovery. That's exciting. That is really exciting. I can't wait. I know we're going to find it eventually. Maybe here in our solar system, maybe we'll see signals. Maybe somebody will call. Hey,
Hmm.
we don't know, but it's going to happen eventually. We are going to discover we are not alone in this universe. Or we will discover we are, which is equally fascinating and deserving of exploration. Either we're alone or we're not. Anyway, so where are you going from here? You've looked at Venus's past and determined it's probably dry, and your indicators are certainly convincing. So you're going to stay on Venus? Are you going to go to Mars? You're going to hang out on the moon? I'm on the moon. See, where are you going to go? Where's your research taking you next? What's the exciting thing that happens in Teresa's life from here?
Mm. I mean, I'm still sticking to Venice a little bit, kind of digging
Okay.
into the atmospheric chemistry more, trying to see what else there is in there. But I am also looking at exoplanets. Like exactly, you were bang on with your questions. I am kind of helping come up with frameworks as to how we know whether we've seen biosignatures or not.
Okay. And so that's gases, that's whatever. It's all the stuff that we talked about a
Hmm.
minute ago. Well, Teresa, this has been a really enlightening and edifying talk. Thank you so much for joining us. I really, really appreciate your taking the time so quickly. This published on the 6th, and today is the 9th. So this is the fresh research. This is the latest word on the gases of Venus and its dry conditions. And we will be back here on Wednesday for Geminid Meteors, Friday for the Sun News with Deborah Bird and Alex Young, and back here on Monday again with Burkhard Militzer. And we're going to talk about oceans on Neptune, oceans on Uranus. We don't know. We don't know. It's an exciting time to be alive, isn't it, Teresa? Isn't this so
Hmm.
exciting? We're gonna find something, and it's gonna be surprising, and it's gonna be eye opening, and it might not be what we're looking for. Thank you so much for joining us. I really appreciate it, folks. Don't forget to like and subscribe. Come and visit us at earthsky.org. Oh, and if you like our lunar calendar, those are available right now in the EarthSky store. You'll find a link at earthsky.org. Remember, folks, there's only one Earth, one sky, EarthSky. We'll see you next time. Thanks for joining us. Bye bye.
Thank you.
Okay, I believe we are clear now.
Mhm.
And you're all uploaded. That was excellent, Teresa. That